Now we will see the various protection schemes that are used for protection of various equipment, power system equipment, right? Till now we have discussed about some various types of relays, okay? So we will now see how to implement them for the protection. First we will start with protection of transmission lines. Depending on the voltage of the transmission line, the protection scheme is going to be present, okay? So for high voltage and extra high voltage line, right? So EHV is extra high voltage. Here more elaborate designs should be used, okay? So here the protection scheme is more elaborate. We are going to use various kinds of protection, various kinds of relays, and there should be some kind of coordination also, okay? So for medium voltage lines, here the scheme is going to be much simpler and most often overcurrent protection is enough, okay? Overcurrent protection is often used and the scheme, the protection scheme is simpler as compared to high voltage lines, okay? As for low voltage, that means the distribution lines. Here mostly there is going to be, we are going to make use of fusers and auto reclosers, okay? So this much is enough. Now here we will consider a simple example to understand these protection schemes, okay? So let us consider a radial system. A radial system is going to have a single source, okay, and the direction of power transfer is going to be in one direction. Now here you have load that is being tapped off at various buses, okay? So these are the bus numbers, and here this rectangles that we have drawn here, these are circuit breakers, okay? Now this is one transmission line between buses 1 and 2, and for this transmission line we have a circuit breaker here, and between 2 and 3 buses also there is a transmission line, between buses 3 and 4 there is a transmission line, and corresponding relays we have. So these are overcurrent relays. Now we will discuss what is the relay coordination that is expected here, right? So between buses 2 and 3, this transmission line, let us say there is a fault that is occurring in this transmission line, right? Now what is the desired outcome? We want this circuit breaker to break, okay? While this circuit breaker, it will also see the fault, a lot of fault current will flow, but we don't want it to operate, okay? Because if this is operating, then there will be no load, that is no current that will be supplied to this load, okay? If only this is operating, this R23 is operating, then this load will be supplied. Okay, these other two loads anyways at buses 3 and 4, whatever load is supplied, that anyways you cannot deliver the power because there is a fault occurring. Okay, so you have to isolate this entire part because now it is the unhealthy, faulty part of the network. Okay, so like we discussed the overcurrent relay, there are different types of overcurrent relay, right? So using intentional time delays, we are going to ensure that this relay will operate first when a fault occurs in this transmission line. Okay, so that is the relay coordination that we want. So this is one example. So here we have considered the radial system, right? From the power is fed from only one side. Now we will take another system where the power is fed from both sides, right? We have two generators here. So here also we will mark the bus numbers. This is bus 1, 2, 3 and 4, let us say. So correspondingly we can mark the relays R12. So basically this is the circuit breaker, okay? So corresponding to the circuit breaker, in order to operate that circuit breaker you need a relay, okay? So this, let us take R12, this we will take R21 just to differentiate, and here we can take R23, this is R32, R34 and R43, okay? Now what are these arrows here? These, they represent that the relays that we have here, they are directional relays, okay? So directional relays will have a directional unit as well as an overcurrent unit, okay? Now once again let us say the fault has occurred in this section between 2 and 3 buses, okay? Now what we want ideally, since power is being fed from both sides, both these relays R23 as well as R32, both of them should break, okay? So that is the desired one. Now for this R23, the backup protection is going to be R12. That means R12 should not operate first. It should operate only if R23 has failed. Okay, because if this operates first hand, then this load will not be supplied. Whereas only if R23 is acting, then this load will be supplied without any problem. Okay, and from here this generator, this load can also be supplied at bus 3 because R32 is breaking off. Okay, so that is the advantage. Now why do we have the directional component here? Directional component will ensure that the relays are protecting only that part of the transmission line which they are intended to protect. Okay, for example, let us say the same fault, if this is here, now this circuit breaker will also break, this circuit breaker will also break if there is no directional unit. Okay, but what is happening? Since the fault current is flowing in this direction, this relay will operate only when fault current is in this direction. This relay will not operate. Why? Because the current direction should be, the fault current should be in the opposite direction for this to operate. Okay, so even if fault current is flowing in this direction, it will not operate. Okay, so in this way this load can be easily delivered from this generator without any problem. Okay, so that is why we use a directional component as well. So this is one example. We will consider one last example. So here we will consider a single generator only, but the loads, they are forming a loop. Okay, and these, here we have the circuit breakers. Okay, but now this circuit breaker which is nearer to the generator end, this is a non-directional relay, that is, it is simply an overcurrent relay. Okay, but here there is going to be a directional component. Similarly, here there is going to be a directional component here as well. So what is the purpose of this kind of protection scheme? Okay, now let us say there is a fault occurring at this point. Now what will happen? If this relay is operating, then the circuit will be broken off, so no power will flow from here, but it will flow from this side. So this relay also, it should operate, right? Now this relay should operate only when there is a fault in this line. Okay, and when there is a fault in this line, the fault current will flow in this direction. That means this relay will operate only when fault current is in this direction, right? So that is why this is having a directional component, whereas the relays near the generator end, they don't need a directional component. Okay, because they are nearer to the generator. There is no transmission line in between the generator and these breakers. Okay, and every other line, let us say if this is where the fault has occurred. Okay, now what we want, desirable thing is this should break down as well as this relay should operate. Okay, so fault current will flow in this direction, so this will operate. Fault current will flow in this direction, so this will operate. In this way both of them are going to operate. Okay, so that's why we have directional units at each of the other buses that are not connected directly to the generator. Next we will discuss the distance protection scheme used for transmission line protection. Okay, so previously we discussed overcurrent plus directional relay protection. Okay, so now we will see the distance protection. So here we have 3 buses. Okay, and here there are the circuit breakers. Remember, these are circuit breakers and these will be operated by distance relays in this case, which is distance protection scheme, right? In the previous case also there was breaker only, but the relay that was operating the breaker, that was an overcurrent or a directional overcurrent relay. Okay, so that's how, don't get confused why we are representing with the same rectangle. Okay, the rectangles we are representing are the breakers, not the relays. Okay, now in distance protection what happens is, this breaker, this relay here R12, this is going to have 3 different zones. Okay, for 80% of this transmission line between 1 and 2, this will offer instantaneous protection. Okay, so you can draw the zone here. This will be about 80% of the line length, transmission line length. This will be zone 1 of R12. Okay, here there is going to be instantaneous response. That means the fault will be cleared instantaneously, almost instantaneously. Okay, And next, the second zone of this R12, the second zone means it will take some intentional time delay before the relay operates. Okay, so that zone 2, it is going to be something like this. Here you have 20% of the remaining line, and here further in the next line also 20% is connected by the second zone of this relay. Okay, so there is going to be some time delay here. So this is zone 2 of R12. Okay, next there will be another zone as well, that is going to be zone 3. So here there is going to be further time delay. Okay, this will cover about 10% of this line. Okay, so zone 1 is going to have an operation time T1, let us say. This is the operation time. And zone 2, it is going to be T2, let us say, and for zone 3 the operation time is T3. Okay, then T1 is the least because that is going to operate fast. Okay, so T1 will be less than T2, less than T3. If the fault is occurring anywhere in this 80% of the line, then this relay is going to operate immediately. Okay, with a certain time delay, there will always be some time delay. Okay, so almost instantaneously it is going to work. Now if in this zone, this 20% and this 20%, if it is if there is a fault, then this will operate only after a time delay, and the next zone 3, there will be further time delay. If there is a fault in zone 3, there is going to be much more time delay before which R12 operates. Okay, so this is zones of R12 that we have discussed. This R23 and R34 are also going to be similar. Okay, so R23 will do what? It is going to protect again the 80% of its own line. Okay, so we can draw here, this is zone 1 of R23. Okay, so this is going to be 80% of this line. Next again, this is going to be zone 2 of R23. So that is going to cover 20% of this line and 20% of the next line. Okay, similarly the zone 3 of this is going to be like this. Okay, zone 3 of R23, it is going to further continue like that. Similarly for R34 you can draw the zones. Okay, so it is going to be 80% of the line will be zone 1 of R34. Similarly zone 2, it is going to continue like that. Okay, now once again if you consider a fault at this point, okay, so we will draw it here. So this is the fault occurrence. Now here it is falling under the zone 1 of R23. So this will operate almost instantaneously. Okay, if this doesn't operate, then the next distance relay will come into picture. See, it is under zone 2 of R12, right? So this is going to be cleared by this relay if this is failing to operate. So it is offering, R12 is offering a backup protection for this fault. Okay, so that is the purpose of zone 2. Okay, now one more doubt that you may have is why only 80% of the line is being protected by R12 without any time delay. Why not the other 20%? So the distance relay, it operates depending on the impedance, right? Now the last 20% it leaves off because if the fault is happening here or the fault is happening here, it will not be able to differentiate. Okay, so that means if you take a point, say here this is point P1 and here let us say this is point P2. Okay, now this relay, it should not operate for the fault at P2. Okay, but it will operate if the zone is extended to this point, because it will not be able to differentiate the fault at this P1 and P2 because they are very close by. So to avoid this and to provide proper relay coordination, only 80% of the line will be protected by each relay, right? So you can write this point, only 80% of line is covered under high speed protection. That means zone 1. Okay, this is because the relay will not be able to differentiate. Here we can take R12, so that will not be able to differentiate faults at P1 and P2, which are on either side of bus 2. Okay, because they are very close by, and the impedance that this distance relay will see, it will be same. Okay, as they are close by, the impedance seen by relay will be same. Okay, so this is some basic understanding of the distance protection scheme. Now, some important points regarding distance protection. Okay, so for short lines, if you remember, we discussed the classification of transmission lines into short, medium and long lines, right, depending on the length. So now for short lines, the arc resistance, which is the fault impedance, it is going to be particularly high for the short lines. So it is significant. So what is the effect of this? When a fault will occur, this arc resistance will be present, which will increase the impedance that is seen by the distance relay. Okay, and the distance relay will operate only when the impedance is below a certain value, right? So if this is the limiting value of impedance, inside this circle, if the impedance falls, there will be operation, but if impedance falls outside the circle, then there will be no operation. Okay, so what will this arc resistance or the fault impedance it will do? It will increase the impedance that is seen by the distance relay, so that it falls in the no operation zone. Okay, so for this reason, what we do is reactance relays are used. Okay, because for short lines, the arc resistance, it is resistive in nature. Okay, so that's why reactance relays are preferred for short lines. And in long lines, what is going to happen? We will prefer the more relays. So why is that? There are going to be power swings in case of long line. Okay, so if you remember, in stability we have discussed, if there is a sudden change in the mechanical or the electromagnetic powers, right, there is going to be a non-zero accelerating power. When there is acceleration, what will happen to the load angle? Load angle or the torque angle is going to increase. Delta will increase. Okay, so now when delta increases, what is going to happen? Delta is nothing but the phase difference between the voltage on the sending end side. Let us say this is Vs and this is Vr. What is delta? If this is taken as 0 degrees, this is delta. So if this angle is going to increase, the difference between Vs and Vr will increase. So what will happen to the current? The current is going to increase. So for a particular magnitude of voltage, here we are assuming the voltage to be not changing. There is no reason for changing. Okay, so for a particular magnitude of voltage, current will increase with delta. That means if delta is increasing, current will also increase. Okay, so what will happen? Voltage is remaining constant while the current is increasing. So what will happen to the impedance? That is also going to change. It will be reduced. Okay, with increasing delta. Okay, so that means the impedance is dependent on the variations in delta. So this is the important point here. So in case of power swings, changes in the power, the delta will change and so impedance will change. Once impedance will change, the impedance relay, it is also going to affect the operation of the impedance relay, right? So for this reason, more relay is preferred because it is less sensitive to this kind of power swings. Okay, so you can write more relays are least sensitive to this power swings and so preferred for long lines. Okay. Now there is another protection scheme which is the pilot relaying scheme. This is for high speed protection of transmission lines. But we are not going to discuss this, just know that there is this kind of relaying scheme for high speed protection. Okay.